What is up, YouTube? This is Mr. King coming at you live from the studio today. So, we are going to be talking about problem-based learning, or PBL, versus traditional methods of teaching. Okay, so let's just start with the basics. So, problem-based learning is all about teaching students content, but not through direct instruction, more through complex and authentic problems, where the students must use their 21st century skills like collaboration, research, etc., and content knowledge to find a solution. And then traditional teaching is what most of us watching this video went through, such as giving the students knowledge through lectures and notes, with labs on the occasion to reinforce the important ideas. So today we're going to be looking at PBL versus traditional teaching with this NGSS standard. So I'm going to be using my middle school lesson, apply Newton's third law to design a solution to a problem involving the motion of two colliding objects. Engage in a scientific argument using textual evidence and logical reasoning to support your claim. So here is going to be our essential question for this unit. How can we design a car to be fast and safe? So here's our question. Here's some highlights of what the students are going to be doing. So with the PBL project, here's how it will work. On day one, you're going to introduce a problem, and the students will make observations and ask questions about the car designs. So what I did is show videos of various cars and having the students do I see and I wonder, just to get them thinking about engineering design decisions. And then Explore 2 is called TinkerCad. Now I'll put a link in the description about TinkerCad, but this is a 3D printing software that students will be using to design their cars. So the point of PBL is that the students should be engaged in things that connect back to the real world. So for our PBL, problem-based learning, the students are actually going to be designing the car using a 3D printer. And they need to design their own car to be fast and safe using what they learn in physics. So just because it's problem-based learning doesn't mean that they're going to be taking notes or not taking notes. So day 3, we're actually going to be going over air resistance and friction so the students understand how those decisions are made in car design. And then we'll start the car design on TinkerCad and go over the safety features of a car. And then we'll take notes on inertia and acceleration, just so students understand motion a little bit better. And then we'll go over how you can modify a car for speed. And then at the end, students will be creating a presentation to justify the decisions they made on their car. And then on the last day, students are going to be presenting their cars with a slideshow and then undergoing racing and safety tests. So the idea is, as you can see in this lesson plan, students are really going to be tying a lot of their learning back into their car. And instead of taking a test at the end, you can still take a test, but we also want to do a presentation where you can see if the students actually understand the physics concepts in their car. And then we're going to compare that to a traditional sequence. And this is a sequence that I've done in the past. I try to keep both of these timelines with 8 days, but in reality, usually PBL will take longer because the students will need more time to make their presentation and make their actual car. So in a traditional learning sequence, we'll also start with an introduction of the unit and maybe get into notes about friction, normal force, and air resistance. And then rather than like starting on a software, students will be answering practice problems on physics concepts with a worksheet, for example. And then just because it's traditional doesn't mean that there aren't any labs. There would be a lab to explore the important relationships like friction and material. That would be an example of a lab we could do, or air resistance and the cross-section of the car. And then the next day you take notes on friction and air resistance and how to calculate them. And then on day 5 you do a worksheet where students calculate the various forces. And then on day 6 you would take notes on inertia and acceleration, similar to the PBL one. And then you'll practice inertia and acceleration through a lab and do more calculations. So I don't want people to think PBL is hands-on, traditional is not hands-on. Both of them have notes and both of them do hands-on stuff. We'll get more into what the takeaways are in a bit. And then at the end, generally you have an assessment. Now, both styles of PBL involve notes and assessment that cover the standards. It's just what you're going to be tying those notes and assessments back to. So, in the traditional method, there's a greater emphasis on math and practicing the concepts in an academic setting. And the teacher's role is more about presenting the content and challenging the students through like math or application questions on a worksheet. Whereas PBL is more about authentic learning with a greater focus on teamwork, using technology, presentations, and culturally relevant pedagogy. So everything that the student learns should be tied back to a real world problem. And the teacher's role, instead of giving the students a lot of the material, the teacher's role is more to like guide students and give feedback and provide them opportunities to reflect on what they learned while they were working on their car, in my example. So I want to give you some resources to start PBL. We're going to go over my middle school physics project where students make the car themselves. The first resource that's essential is TinkerCad. This is the bread and butter of 3D printing in education. It is very user friendly and it does take a day to get used to, which is why my first day I had students just playing with the software. And I also have made a car template that I'll put in the link description. But a lot of schools I've learned have huge CTE budgets and small science budgets. So what I've learned is to have the CTE budget, have a CTE teacher, or have a CTE support person who could modify or add a 3D printer into the CTE budget. And here are two cars that my students made. And at this point, I do want to go over what my students did. So here's an example of something I posted on a Google Classroom. So I gave the students a template, I gave them the objective, the rubric, and I posted this template for their presentation on Google Classroom, just so students know what the expectations are of our project, that unit. And the nice thing about Google Classroom is it's very handy if students have laptops because they'll use Google Slides, Google Forms for exit tickets, and Google Classroom is a great way to modify students' work and see what they're doing while they're working on it. So I recommend this resource because you can assign slides for a PBL presentation and then check their understanding while they work. And here's an example of a template slide just to see how well my students understand the physics concepts. The last research I want to offer is a research article that I found very insightful. It's called The Pros and Cons of Problem-Based Learning from the Teacher's Standpoint. So this guy, Luis Ribeiro, he goes over his experience switching from traditional teaching into problem-based learning. And at first, it was very hard. There was a big workload increase because problem-based learning requires a lot of planning. And the first time you're doing it, it's a little weird because the role of the educator is to be more of a guide. And the educator has to embrace less control over what the students are learning because a lot of the students' projects will go into fields or go into ideas that you didn't expect and you may not be an expert in. However, overall, there were gains in engagement, motivation for science, and a greater understanding of the principles in their project. And that brings me to the conclusion. So a reason why a lot of educators switch to PBL is because of long-term knowledge retention and application level understanding. So when a lot of the students are working on cars, like for my example, they're really understanding why a car has a spoiler or how opening the window, opening your hand outside will make the car a little bit slower. They'll understand those ideas more in depth, but something that they may lose is knowing how to calculate friction in a force body diagram because a lot of it we tie back to the real world with engineering principles and a lot of the academia that a lot of physics teachers are used to is not as important in PBL. And I want to note that execution is very important for PBL. A lot of studies have shown that if the students are constantly engaging in reflection and metacognition, that that leads to the biggest gains in PBL outcomes. And based on my experience in middle school, the students need explicit timelines because a lot of PBL, the students can dilly-dally. So it's better to try and chunk different days and sometimes change the pace just to keep the novelty for the students' engagement. Thank you so much, everyone, for staying with me the whole time. Here are all my sources. Please like, comment, subscribe, and let me know if you have any questions in the comments below. Thank you so much.